Hello everyone, I'm Wei Weng Kui. Today we're going to talk about DCI backbone networks. By 2020, 90% of services will be cloud-based, including personal services, home services, enterprise services, and IoT services, driving traffic growth between DCs and between DC and users. DC to user traffic is set to increase threefold over the next 5 years, while for traffic between DCs, this increase will be closer to fourfold. Effectively handling DC traffic on the backbone networks has become a genuine challenge. Requirements on backbone networks in the cloud era include low latency, low cost, services on demand, easy O&M, and smooth evolution. Now let's go over these requirements one by one. First, rapid DCI traffic growth directly affects network transmission costs. Evidently, increased transmission volume requires more OTU ports. As we know, one of the essential driving forces behind cloud computing is its low price point. Cloud computing provides low-cost IT computing resources, and so it follows that the network side of cloud computing needs to be cost-effective as well. Comparing 10G, 100G, and 200G technologies, we can see that 200G single wavelength is more cost-effective than 10G or 100G. Therefore, using 200G technologies for backbone DCI is more advantageous. Second, cloud services pose requirements on latency. For example, high-frequency transactions, videos, and cloud desktops, CDNs, require 1 millisecond, 30 millisecond, and 50 millisecond latency respectively. These cloud services require not just low latency, which is basic, but also measurable latency, which is the basis of service path selection, and manageable latency, which is fundamental to latency-based path selection and latency optimization. Third, cloud private lines have strict requirements on TTM. For example, one OTT customer required a 6x100G service from Shenzhen to Hangzhou in 10 days, but operators can only deliver the service in 4 months. As a result, the OTT customer had to construct its own backbone network. Meanwhile, e-commerce shopping events such as November 11th burst sales amount as well as required bandwidth. Being able to provide larger bandwidth on such events and revert back to normal bandwidth after the event has become a key requirement in service bandwidth adjustment. Fourth, as backbone DCIs transport key services on the backbone networks, reliability requirements are very high. It is still common that customer services get interrupted because of faults on operators' networks. For example, 70% of OTT Company T's service faults were the results of faults from the operator's network. OTT Company A requires millions of US dollars in compensation for one DCI network interruption. The ever-increasing scale of networks requires easy O&M. One O&M engineer in an OTT company can maintain 10,000 servers, whereas an operator O&M engineer can only maintain 20 to 50 servers. With such a vast difference between the two, operators need automatic networks with easy O&M. Finally, DCI networks should also be able to evolve, and the following qualities are required: simplified O&M, software-defined, flexible optical layer scheduling, flexible electrical layer scheduling, large bandwidth and low latency. There are 2 solutions available for constructing DCI networks: constructing new DCI backbone networks and adding DCI nodes to existing networks for reconstruction. Constructing new DCI backbone networks is generally the better choice, for reasons I will now explain. First, 100G, 200G transmission performance is better in pure coherent networks, with reduced regeneration sites and CapEx, and supporting of evolution towards 200G. Second, new networks that are DC-centric with one-hop direct routes can maximize latency optimization while providing both latency measurement and latency-based route selection through TSDN. If bandwidth adjustment is required on newly built DCI backbone networks, private line customers can deliver commands through the self-service portal for hitless adjustment in one click. Any systems uses the ODU Flex plus GHAO technology for smooth bandwidth adjustment. Fourth, in terms of O&M, New mesh networks are DC-centric and have ASON features integrated on the SDN centralized control layer. These new networks are resistant to multiple fiber cuts, have greatly improved reliability, and support full lifespan E2E online network analysis, planning, and management. Lastly, a new DCI backbone network is a better starting point for the all-cloud era in that it can align with the latest solutions in the industry by leveraging the following strengths. 1. Large bandwidth and low latency. Single wavelength channels are improved to 200G for large network latency. DC-centric one-hop reachability achieves low latency. 2. CDCG ROADM enables optical layer wavelength adjustments and will evolve towards OXC. 3. OTN scheduling is implemented on the electrical layer, and OTN clusters are used for distributed extension when capacity is insufficient. 4. The SDN platform uses an intelligent management and control platform and Open NBI to support open service innovations. 5. In terms of O&M, network resources and performance are visualized to achieve fault locating in minutes. To summarize, the advantages of constructing new DCI backbone networks are as follows. 1. Pure coherent networks reduce regeneration sites. 2. DC-centric one-hop reachability optimizes network latency. 3. Full-service provisioning shortens TTM. 4. New DCI backbone networks support flexible bandwidth adjustment. 5. New DCI backbone networks support higher reliability and automatic O&M. 6. New DCI backbone networks align with the latest solutions in the industry and are excellent starting points for all cloud networks.